Hi. So I'm Sam Lawler. Thank you so much for inviting me here today. It's a real honor to be here. So I'm going to tell you about the structure of the Kuiper belt. I was asked to give a talk on a review talk on the Kuiper belt, and this is the aspect of the Kuiper belt that I know best. So a quick outline. First, I'm going to give you a brief history of discoveries in the Kuiper belt and how that has shaped our theories about how it was built. Then I'm going to talk a little bit about so by looking at the structure in the Kuiper belt, we know that Neptune moved quite a bit. And Neptune caused a big mess of the proto-Kuiper belt. And what we're seeing is kind of the blood spatter on the wall after the crime. And then I'm going to talk a bit about observational biases, which are important to any part of astronomy, but they can be especially nasty in Kuiper belt studies. So I want to talk a bit about that. Some of what we can learn about studying the very detailed structure of the Kuiper belt, I'm going to give a few highlights there, including some thoughts on Planet 9. Highlight a couple of lingering mysteries about the Kuiper belt that I hope will be solved in the next few years, and talk about how our Kuiper belt helps us understand other solar systems. So Pluto is the original Kuiper belt object, and it was discovered several decades before the second Kuiper belt object, which kind of explains why it was thought to be a planet for so long. We've gotten to know Pluto a lot better in the last few years, especially a couple of years ago when the New Horizons mission flew past Pluto and produced these gorgeous pictures of the surface. I think it's kind of funny that I wrote an entire paper about the orbit of Pluto, and I never once thought about what it looks like. and it's beautiful. There's geology, there's mountains, there's an atmosphere. It's a tiny little world, but it's not a planet. So, the first clue that it was not a planet is its extremely tilted, very eccentric orbit. Relative to the rest of the planets, it's got a very different orbit. It was discovered very early on, back in 1964, through numerical simulations, that Pluto is in a mean motion resonance with Neptune, and that's how it's managed to stay so eccentric for the age of the solar system. Even 20 years ago, computation resources had increased enough that you can look at a much longer integration. And so this is looking down on the solar system in a frame that's co-rotating with Neptune. So this is an ideal way to look at Pluto's orbit relative to Neptune. So you can see that Pluto actually crosses Neptune's orbit, but is protected from close encounters because of this resonance. And where it comes to pericenter actually changes over time. It's called libration. So the Kuiper belt was originally hypothesized to be this very flat. So I'm going to show plots like this a lot. So eccentricity and inclination versus semi-major axis in the Kuiper belt region. So outside 30 AU. So originally the Kuiper belt was hypothesized to be this very dynamically cold, low eccentricity, low inclination disk of planetesimals outside Neptune's orbit. But even with the very first discovery, it's pretty far outside what was expected. The second one was discovered in 1992. By 1996, there was a handful of them, and you can see that there's basically nothing in this dynamically cold area where the Kuiper belt was expected to be. Over time, this has built up. This is what the Kuiper belt looked like 10 years ago. This is what it looked like yesterday. So this is about 3,000 Kuiper belt objects that are known. So this is pulled from the Minor Planet Center database, which is the repository for all small bodies in the solar system. So everything that's discovered is reported. I'll talk about some problems with that later on. So here's another plot that highlights the different dynamical classes within the Kuiper belt. Again, inclination and eccentricity versus semi-major axis. Here's Neptune's orbit right here. And one of the first things that jumps out is there's a lot of Kuiper belt objects that are in mean motion resonances. So all of these dark points are in the mean motion resonances with Neptune. And they're much higher eccentricity than most of the Kuiper belt. The light blue points are what's called the classical Kuiper belt. And these are the closest to the originally hypothesized Kuiper belt. And then there's this structure out here where at larger semi-major axis, Kuiper belt objects have higher eccentricity. And this is because Neptune emplaced them. So this sort of curve is where Kuiper belt objects have had a dynamical interaction. They're dynamically coupled to Neptune along this curve. The red points are Kuiper belt objects that have higher eccentricities than this curve. So that means that they will have a close encounter with one of the giant planets sometime in the next few million years. So they're unstable on long time scales. So the way that the Kuiper belt was emplaced, so imagining that there's this massive proto-Kuiper belt with lots of objects in the early solar system, and what happens is over time Neptune starts scattering a few of these. So Neptune scatters one inwards. It scatters around between the planets. Sometimes it'll get scattered back out by Neptune. But if the Kuiper belt object manages to get handed down to Jupiter, Jupiter has enough mass that a scattering event with Jupiter is likely to completely eject it from the solar system. So the net result is that Neptune overall is scattering more in than out. And so Neptune moves outwards. And this was the first explanation for Pluto's orbit. So as Neptune scatters planetesimals inwards and moves outwards slowly, its mean motion resonances also move outwards. And this is how Pluto got trapped in a mean motion resonance, in the 3-to-2 mean motion resonance, as it moved outwards. And once it's trapped in there, its eccentricity gets pulled higher and higher. And a good Canadian analogy for this is like a snowplow. So that's smooth migration. So another different explanation for how all of these objects got trapped in mean motion resonances is the Nice model. So this is the proto-Kuiper belt. The 4 giant planets start in a much tighter configuration. So now Neptune's out at 30 AU, and they're all inside 20 AU. And they sort of jiggle around a bit chaotically as they interact with each other, and they interact with these planetesimals. And at some point, there's a giant scattering event in just a moment. And the proto-Kuiper belt is pretty much completely destroyed as Neptune gets flung outwards onto this very eccentric orbit. And then as Neptune's orbit circularizes by dynamical friction with these Kuiper belt objects, a lot of them get trapped in mean motion resonances. So there's these 2 totally different ways to explain why there are so many Kuiper belt objects in mean motion resonances. One thing that we've been ignoring so far, and often gets ignored in Kuiper belt studies, what about observational biases, right? So these are discoveries, but there's some very important observational biases to take into account here. So because Kuiper belt objects are seen in reflected light, their brightness drops off as 1 over r to the 4th, right? So if this Kuiper belt object is 10 times further away at aphelion than at perihelion, it's going to be 10,000 times fainter. And just because of Kepler's laws, it spends more time out here. So when you get high eccentricities, it's very unlikely that you're going to detect them. Another important observing bias, so these are all plots looking down on the solar system. Here's Neptune. And these are different mean motion resonances. And where on the sky Kuiper belt objects come to pericenter depends on what mean motion resonance they're in. And where they come to pericenter is where you're most likely to detect them. So where you look on the sky, can greatly influence what mean motion resonance you're most sensitive to. So it's important to keep track of that. One last important bias to keep track of is where you look on the sky and detect Kuiper belt objects is just as important as where you look and don't detect Kuiper belt objects. And that's basically never reported. And I'll talk about this a little bit more in the context of Planet 9 later in the talk. So the solution is to very carefully characterize and publish your survey's biases. I'm part of the Outer Solar System Origin Survey, which is a large survey that does exactly this. And it's a large collaboration that actually includes a significant fraction of everyone who works on Kuiper belt. OSIS uses Megacam on CFHT, which is it's a physically huge camera, huge CCD, and it's a square degree on the sky. So it's perfect for discovering new Kuiper belt objects. Actually, discovering Kuiper belt objects is an interesting kind of astronomy because they actually move on the sky minute to minute. So it's both more fun in some ways and a lot harder in other ways. And you might just initially you might think, oh, it's because they're orbiting, but it's actually because the Earth is orbiting that you can see them moving on the sky. So we first observe at 2 months before opposition. We observe at opposition, which is when they have the most reflex motion on the sky and are easiest to detect, and then again a couple of months later. So this 5 months gives us a very good baseline on their orbits, and we can predict ahead. And then we observe them again a year later and a year later. So this gives us the most precise orbits of any Kuiper belt study. So here's a nice animation showing how one of our survey blocks is filled in on the sky. So the date's up here and the moon phase is up here. Most of the observing is done in dark time. And each of these squares is one pointing with Megacam. So here's some of the Kuiper belt objects that are identified as the survey progresses. You can see these lines where one Kuiper belt object is moving over time. Because we have this 5-month baseline, we're able to predict really well where each of these Kuiper belt objects is going to be 1 year later, even if they're in really strange orbits. That's been a problem with other surveys where they don't consider retrograde orbits or very close in or very far out orbits that would move at a different rate. So now we're moving forward in time. All of these 5-month baselines are used to predict where the Kuiper belt object will be in another year, and then we can specifically target all of them. So even one like this that's way off from the bulk of Kuiper belt objects, we still manage to track it a year later and pin down its orbit really precisely. So we know for each block on the sky, we know what our biases are. We know how deep we could see, and we know how well we tracked everything. So now we can take a model and forward bias it and compare it with the actual survey detections. So I'm going to show this. So OSIS is it just finished a couple months ago. So we haven't done all the analysis yet. I'm going to show you what we did for CFEPS, which was kind of a precursor to OSIS, using the same strategy. So I'm just talking about one population here. So we do this for each subpopulation within the Kuiper belt. So this is the Plutinos, which are objects that have orbits like Pluto. They're in 3-to-2 resonance with Neptune. So we're looking down on the solar system. Here's Neptune. Each of these blocks shows one of those big blocks on the sky and sort of their relative depths. Let's see. So we build up a model. And so this is another way of looking at it in cumulative fractions in different orbital orbital distributions and magnitude distribution. And that's what it would look like on the sky. Then we take our survey biases and apply it to this distribution. And so then we get a distribution of simulated detections that have the same biases as the real survey detections. And we can detect as many as we want because there's no TAC to tell us that we can't. And so then we compare this statistically with the true detections, and we get really powerful constraints on what the de-biased Kuiper belt has to look like in each population. So this is our real detections in eccentricity, inclination versus semi-major axis, and this is the de-biased distribution. So you can see there's just a very few detections, and especially further out, there's only a couple of detections out here. But because the biases are so strong against detecting these, there has to be many objects out there in order just to get one detection. And here's another way of looking at the de-biased Kuiper belt. So each of these little tiny dots is actually the real number of Kuiper belt objects bigger than 100 kilometers in their statistical orbital distribution. So this is what the Kuiper belt looks like. Pretty cool, with no biases. So the detailed resonance structure tells us about how Neptune migrated. So when we study the structure within each of these resonances, this is how we will learn exactly what Neptune did, whether it had a chaotic migration or a smooth migration. So just to highlight a couple of examples. So looking at the de-biased number of objects in each of these three resonances, we find that the prediction from both the smooth migration and chaotic migration, the population ratios do not match what we actually see in the end. So so we need another model. Like, clearly neither of these models is giving us the right answer. So one that has been proposed recently is grainy migration. So in this, instead of Neptune smoothly migrating outwards, we put basically a bunch of Plutos, like thousands of Plutos, in the Kuiper belt, so that as Neptune migrates outwards, instead of smoothly scattering these little tiny Kuiper belt objects, it has little jerks in its outward migration, and this dramatically changes the structure of the Kuiper belt as it's built up. Let's see. So this is telling us, so if this is true, this is telling us about the initial distribution of planetesimals and what the sizes were like. So this is not only a constraint on how Neptune moved, but it's a constraint on how big planetesimals can form. So looking at, so this is a detailed analysis that we did of a Nice model simulation. This is a detailed analysis of a grainy simulation. So the biggest difference happens in these fingers of resonances. So so Neptune scatters Kuiper belt objects outwards on this eccentricity semi-major axis curve. But what happens once Kuiper belt objects get caught in a resonance is they can cycle up and down in eccentricity and inclination through Kozai cycling. So they can get pulled down into this high paracenter, low eccentricity space that otherwise would not be populated. And as the resonances march outwards, in grainy migration, we find that there's actually a lot of dropouts that are on the sunward side of the resonances. So there's these sort of trails of non-resonant objects behind the resonance. In the Nice model, on the other hand, we find that the dropouts around the resonances are rather symmetric. We call them beards, resonant beards. Which is appropriate since one of the main proposers of the Nice model has a big beard. So by studying these resonant fingers, this low eccentricity, high paracenter population, we should be able to tell the difference between these two very different models. So in order to do this, we need to debias the OSIS survey. So we've already done this for CFEPs, but there weren't enough detections. OSIS has far more. OSIS has 800 detections of new Kuiper belt objects. And so you can see that this low eccentricity area is extremely sparsely populated, right? This is where there's extreme observational biases against detecting anything here because it's all high pericenter, right? It never gets close to the sun. It's never very bright. So what I'm going to be doing soon is working on debiasing the near resonant population and comparing it. With both of these models to see if we can put some sort of handle on what actually happened. Okay, so here's the fun part. So what can we say about Planet 9 from the OSIS survey? So Planet 9, which I'm sure all of you have heard about if you've been in the solar system for the last year. So Planet 9 was proposed because looking at the Minor Planet Center database, there are 6 Kuiper belt objects that have very high pericenters and large orbits, and they're all clustered on one side of the solar system, which is kind of suspicious. So Planet 9 was proposed as a dynamical way to keep these all constrained over on one side of the solar system. But I'll just start off by saying that this is from the Minor Planet Center database, which is full of biases. So for example, all of these are detected over on one side of the sun. We don't actually know if anybody looked over here at all and didn't find anything, or if nobody looked there, right? So there's possible observation biases right from the get-go. Here's another way of looking at this. This is eccentricity versus perihelion. Here's Neptune for reference. And this was really good work by a survey that's been focused on finding the most distant possible Kuiper belt objects. So all of the red ones are ones that they found. So you can see that, especially, so Sedna is a famous one, and this more recent discovery, they have extremely high pericenters. They're pericenters at 80 AU, so they're always extremely far away from the sun. It's very hard to find these. It's also in the land of extreme unpublished observational biases. So you can see that the number of Kuiper belt objects drops off dramatically when you get to this distance, but is that because there's a real drop off, or is that just because of biases? And we don't know because the biases are not published for these surveys. So taking our well-characterized survey where we know the biases, what can we say about Planet 9? So we did 3 different experiments. The first experiment was a numerical experiment where we take this. So Planet 9 is proposed to be 10 Earth masses, so we put it on its purported orbit and emplace the Kuiper belt in the presence of Planet 9. And so what does it do to the distribution of distant Kuiper belt objects, and would we be able to detect this with OSIS? And because we have a well-characterized survey, we can actually answer this question. So this is pericenter distance versus semi-major axis for 3 different models of the Kuiper belt. So the control is just the 4 known giant planets. And you can see that, so all of the orange points here. So you can see that they all stay at very low pericenter, which makes sense because they have to be scattered outward by Neptune. So they have to stay fairly close to Neptune. When you add in Planet 9, so the blue and gray points are 2 different Planet 9 models. When you add in Planet 9, the pericenters get pulled up at large semi-major axes. So this is a very strong signal, but it's in this high pericenter population, which is going to be very hard to detect. So looking at inclination versus pericenter distance, again, we can see that the inclinations with Neptune stay fairly low, with just Neptune stay fairly low, but when you add in Planet 9, there's some of the Kuiper belt objects get pulled to very high inclinations. Some of them even get pulled retrograde. So there should be a large population of high paracenter, high inclination Kuiper belt objects, which initially I was really excited. I thought for sure we'll see this with OSIS. So we take this model, we put it through the survey simulator, and so another way of looking at this. So this is the semi-major, so these are cumulative distributions in semi-major axis, inclination, and paracenter distance. This is basically just showing that there's a really big difference between the orange line and the blue and gray lines, right? So after running it through the survey simulator, we find that there is not really a big difference anymore, which is really disappointing. So that means that we actually would not be able to tell the difference between a solar system with Planet 9 and a solar system without Planet 9 with using this distant population, which is annoying. But one thing that was really interesting that we found with this simulation is that, so these are showing different orbital angles, and you can see that they're completely randomly distributed. So we do not see any sort of orbital clustering as is proposed for Planet 9. So either this signal is not present, or it's completely overwhelmed by other Kuiper belt objects. So another numerical experiment that we did is to just integrate. So what happens if we take these 6 clustered Kuiper belt objects and integrate them in the presence of Planet 9? So here's Planet 9. Here are the 6 clustered Kuiper belt objects, and there's clones within the orbital uncertainties because these are very distant. They have large uncertainties. And then we integrate forward in time. And what should happen is they should all stay clustered over here for the age of the solar system. But they don't. So within a billion years, the orbits are completely smeared out over time. So we find that Planet 9 does not even it does not keep the Kuiper belt objects aligned that it is supposed to keep aligned, which was the entire reason that it was proposed. So the third experiment is a completely observational one. So because we have this very powerful survey, we were able to detect an independent sample of high paracenter, large semi-major axis Kuiper belt objects, and which is the population that is supposed to be clustered, as is in the Minor Planet Center database. So are they aligned by Planet 9? Let's take a vote. How many people think that they will be aligned? Ooh, I convinced you. So looking, yeah, they're not aligned at all. This distribution of orbital angles is completely consistent with random. So yeah, there's absolutely no evidence in the discoveries from OSIS of any sort of orbital clustering. So just to summarize all of this, we find that Planet 9 does not produce alignment in simulated Kuiper belt objects. It does not keep known Kuiper belt objects aligned, and newly discovered high paracenter distant Kuiper belt objects are not aligned. But there's some interesting lingering mysteries here. So another recent study looked at the mean plane of the Kuiper belt. So these little plus signs are a prediction of what the mean plane should be just based on secular theory and where the 4 giant planets are. And basically what they find is that within the main Kuiper belt, the mean plane, when you average all the Kuiper belt objects together, their mean plane matches this theory really well. But when you look out at large distances, out at like 100 AU, they do not. They're several degrees off from the mean plane. And this could be explained by a Mars-sized body out in the Kuiper belt, which at 100, 150 AU. And this would be, so this is kind of a slimmed down Planet 9. Well, Planet 9 is supposed to be a 10 Earth mass giant planet out at 500 AU. This Mars-sized body at 100 AU is a little bit more plausible and matches observations. Another mystery is, so if there isn't a planet 9, how do you get these very high paracenter Kuiper belt objects out there, right? Planet 9 is very good at pulling up the paracenter distances, and these guys, they never get closer to Neptune than like 50 AU, right? They are not scattering off of Neptune. So how do we do that? Well, luckily there are about as many different theories as there are high paracenter Kuiper belt objects. There's possibility for a rogue planet that was ejected, no longer present in the solar system. There's planet 9, which is just one of these many theories. It could be a stellar flyby. It could be something to do with the birth nebula of the sun. There's many different theories. So as we discover more very distant Kuiper belt objects, it will become more clear which of these theories is the best one to explain the distribution that we see. So let's take a step back a few parsecs and pretend that we are on, we have some kind of super ALMA on a distant planet, and we're looking back at the solar system. So if we could, if we had really much better detection limits than ALMA, and we ignore the asteroid belt, this is what our solar system would look like. So what I think is really interesting about this is we know that, so I've been talking about resonant Kuiper belt objects for this entire talk. So almost a quarter of the Kuiper belt appears to be in resonances, but you don't see any of that structure at all. You'll often see pictures where there's two bright lobes for the Kuiper belt, but when you look at the overall distribution, you actually don't see that at all. It's completely dominated by this very narrow ring. The resonant objects are just too spread out over a large area to be able to contribute much flux in millimeter wavelengths. So what's interesting about this? So if we think about debris disks in other solar systems, so debris disks are dust that's visible in other solar systems, and where there's dust, there has to be planetesimals that are grinding down. So it's kind of an indirect way of finding Kuiper belts in other solar systems. So if we compare our solar system, it's not wide like many of the debris disks that we see. It's actually a very narrow ring, very similar to the Fomalhaut system. So Fomalhaut has been proposed to have a shepherding planet, or there's some papers have proposed that there's 2 shepherding planets that are that have to be present in order to hold this very narrow ring. But in our Kuiper belt, we just have Neptune, right? And this very narrow ring is actually confined by 2 resonances. The 2-to-1 and the 3-to-2 mean motion resonance is where the bulk of the Kuiper belt is. And it was produced by Neptune migrating. So does that mean that that seeing narrow rings in other solar systems, is that a sign that migration has happened? So in order to answer this, we need to discover a lot more planets, or a lot more solar systems with both a debris disk and a planet. GPI and Sphere are both doing very good jobs of finding lots of narrow ring systems like this. Not so many planets have been discovered, but lots of narrow debris disks. And then from studying the structure in our Kuiper belt, we can say hopefully we can say whether or not this narrow ring formed because of a chaotic large-scale migration or a smooth, slow migration. So just to summarize everything, so the structure of the Kuiper belt gives us a chance to view the detailed orbital structure of planetesimals. In other solar systems, we only see the dust. We don't know exactly where the planetesimals are or what their orbital structure is like. But here, it's the opposite. We're seeing the orbital structure of the planetesimals and not seeing the dust. We have to simulate the dust. But we know because of this detailed orbital structure, we think that we can back out what happened to Neptune. The one huge point I want to make is to beware of observational biases. They can be accounted for and characterized well and published and shared, and then if all surveys did this, then the Kuiper belt would be a lot less complicated place. Again, by studying the very detailed structure of the Kuiper belt, we're going to be able to figure out exactly what kind of migration happened, and hopefully we can apply this to other solar systems and see whether smooth migration or chaotic migration is common in other systems. And in the next few years, LSST is predicted to find thousands of new Kuiper belt objects. So we're going to learn a lot more about the high pericenter population and the distant Kuiper belt, and be able to put some really good constraints on what Neptune did. So thank you. Sorry I'm a little early.
How much mass is there in the Kuiper belt?
How much mass? There's about an order of magnitude uncertainty, but a tenth of an Earth mass is about is what I've seen mostly, plus or minus.
So you're taking planet 9 out. It's a tenth of an Earth mass.
Yeah. The proto-Kuiper belt would have been much more massive. It could have been tens of Earth masses, but what we're seeing is very small. Yeah.
Putting another nail into the coffin for Planet 9, if you saw David Nashorny's talk last week at BPSBD.
Oh, did he give a good?
He said the Jupiter family comets are totally inconsistent with Planet 9 at that location. They would have to be much further out, or else you would disrupt the Jupiter family comets.
Yeah, David Nesvorny has done a lot of really good simulations that parallel the simulations we've done through OSIS, yeah.
So can you put a probability on excluding Planet 9 from what you have done? I think many of us, when they came out with it from outside, were very skeptical, and it was kind of like armchair astronomy.
Yeah.
Now it's huge, and it's probably in kindergarten course at this point. So if you can put a probability on it, I think that would be very helpful.
Yeah, I mean, so from what we did, the only statistical thing I could really say is that the distribution of orbits that we see is completely consistent with random. There's no clustering, right? So I can't rule out clustering, but I can say that it's consistent with no clustering, right? So yeah, but I'm hoping to do a little bit more statistical analysis now that we have the full OSIS results. So.
Great talk. So on the third point from the bottom, need more planet
yes.
discovery. So Tiffany Mesh, I thought you were aware.
Yeah, I saw her talk.
Where she showed that there's several significance difference between disk planet systems with debris disks and those without. And so does this help answer your question, or like what more data would be needed? Yeah, so her result was very specific to directly imaged planets and disks, right? So it's a very specific population of sort of young, very large, like multi-Jupiter mass distant planets. So there's been several different analyses that try to look at debris disks and hot Jupiters, debris disks and Kepler systems, and none of them have found a strong correlation. So this is the first study that I've seen that I believe there's actually a correlation there, which is really nice. But again, I don't know how applicable it is to all systems. It's just this one very specific subclass right now. But I'm looking forward to seeing more.
Okay,
Sort of continuing in the same vein, how close are we to really discovering a Kuiper belt equivalent around any nearby stars?
Oh.
Are we orders of magnitude away? Or?
Yeah, so looking at the bright, so I don't know the numbers for ALMA. I know for Spitzer, if we're about 2 orders of magnitude off for asteroid belts, and about 3 orders of magnitude off for Kuiper belts. So we still have a ways to go.
Any more questions?
Well, speaking of coffin nails, so Neptune did migrate, and the issue is what was the form of that migration?
Yes.
So how many years away from answering that question are you?
Oh, that's a good question. Well, let's see. So I think that I think that some of this upcoming analysis that we're going to do with the beards and trails question, I think that's really going to be a powerful constraint. We have the data. We just have to see how much we believe the debiasing, right? We have to basically, the best way to do this is going to be to forward bias these models, and we just might not have enough particles in the models to get a good statistical answer. So basically, we just have to throw more computer time at it at this point. So I think using OSIS data, I think we'll have a fairly believable answer within a couple of years. I hope.
Okay. With that, time for the first question session. Thanks again to Sam.